and data. There are lots of problems, but we are here to solve them.
Thank you, Uli. And I would like to invite Rob Kursinski, our last speaker for this session. And he's going to talk about atmospheric structures observed in the lower troposphere with PlanetiQ radio occultation data.
Okay, I'm going to talk about work we're doing in the lower troposphere with the highest NR observations we've been generating at PlanetiQ. Quick outline of the importance of the lower, just a reminder of the importance of the lower troposphere, RO's unique ability to characterize it, some key challenges, overview of new retrievals we're developing, examples with some very closely co-located high-resolution sondes, an ability to observe convection that I hadn't realized, and the need for, I'll explain this later, three-dimensional retrievals, some preliminary conclusions and next steps. So this slide is just a reminder, the boundary layer is really important. The National Academy of Sciences directed NASA to focus some effort on creating ways to measure the boundary layer for the reasons it's important and because we're really bad at measuring it over most of the globe. The thing is, one of the things that keeps driving me is that RO has really unique features for measuring the boundary layer, unlike anything else, because of the long wavelengths, the high vertical resolution, the insensitivity to clouds and the underlying surface conditions. So this is one of the things that keeps me motivated because it's very important, and RO has unique features. We've really got to try and do our best to extract that information. So I've listed 5 key challenges. We know that the NWP is avoiding the RO in the lower troposphere boundary layer, and I'm not going to talk about that. The other 4 I'm going to talk a bit about. I'll show the RO is underestimating the large bending angles in the lower troposphere boundary layer. We're trying to reduce the noise on these, and I'll talk a bit about that. And of course, come up with uncertainty estimates because you need that to assimilate it. And trying to come up with better vertical resolution, driven in part by trying to see the top of the boundary layer and also detect the ducting, as Faye talked about. This is a quick example of a nice profile. Can I see this? Yeah. This is us. GDAS is in red, and ERA5. The PlanetiQ and the ERA5 agree pretty well. The GDAS doesn't really pick it up in this case. But one point here is we tracked the signal down to -160 straight line. So this bending angle should have actually been much larger than this peak bending angle. The fact that we tracked down, that implies a bending angle around 0.06. We got to 0.025. So we did histograms. This is like a year ago. We did some histograms of these are different latitude bands. The GPS, yeah, this is the GPS is in red. This is AVN Prof, which is from NOAA forecast, and you can see the problem is the RO is missing the high end of the large bending angles at these low latitudes. And so this has really been driving me to figure out what is going on here and can we do better. Now, we are seeing in the PlanetiQ data a lot of very deep occultations, and getting down to -170, which I've drawn the straight line here, is about 0.07 radians. And if you look back here, you hardly see any RO greater than 0.04 down here. So But what that says is the information's in the observations. It's not getting through the retrievals. And again, here, there's roughly a third of the occultations here should be seeing bending angles bigger than 0.07 radians. That's what the criterion is for these dots. And they're not getting through the retrieval process. So we've been working to capture the large bending angles, trying to reduce the noise and come up with, and simultaneously have higher vertical resolution, which you need to see the big bending angles. So we've developed a phase matching retrieval capability. And one of the nice features here that I think is really important is we have high SNR at L1 and L2. there's a lot of diffraction noise in the lower troposphere, and it really helps to have two wavelengths to try and sort out what is signal and what is noise. So, so I only trust the ones where where I see the same peak in the SNR at both L1 and L2 at a given bending angle and impact height. So this is an example of a profile that happens to have, let's see. So we got a pretty deep signal. In fact, it's quite deep, but it's a quite strong signal right here. And that maps into, this is bending angle in the horizontal axis and impact height in the vertical. And this, I don't know if you can, yeah, you can see it. There's energy out here, there's coherent energy, and we're trying to get the bending angle to retrieve that. So on the left is L1 and L2. This is on the horizontal axis is bending angle, and on the vertical axis is what's coming out of the phase, the SNR is coming out of the phase matching. On the right, sorry, in the middle, this is, I've multiplied L1 and L2 in this case to try and get to pick out the peaks that are common to both. And on the right is the bending angle profile. So as I'm going to step down in 12.5 meter increments. And you can see in the center profile in particular, the large bending angle, it happens to have the largest SNR at that time. And so this max algorithm on the right is finding that as the solution. And this multiplying by L1 and L2, it tends to clean up some of this horrible noise. This what I think is speckle noise. This is coherent. We're sending coherent signals through a turbulent media, and it's causing a lot of diffraction, a lot of self-interference, which is one of the challenges of the lower troposphere. And so this is, oops, sorry, I'm going the wrong way. This is the power on the left panel. The next panel is going to show you the power on the left panel that did not make it into the right panel. So quote unquote diffraction noise, speckle noise. And so there's a lot of, where the signals are strong, there is a lot of noise. Where the signals are weak, actually, there's not so much noise. And this is the thermal noise. So when we naively went to high SNR and thought, that's going to help everything in the lower troposphere. The problem is we're not dominated by thermal noise. We're dominated by speckle noise. And the trick is now going to become how do we best deal with this speckle noise? But hang on a second. Oops. I do want to make a point again. When these larger bending angles are weaker and the speckle noise goes down, and so I'm optimistic that we can actually pick out these larger bending angles. So now I'm going to show some close co-locations with radiosondes, high resolution radiosondes. Based on one figure I'm not going to show, I made this very tight, 60 meters, because there's so much variability. I was really trying to get them co-located, and particularly in space. The problem is, again, this is 2 needles in a haystack. So out of 30,000 occultations, we get about 1 in 1,000 that met this criterion. So this, I'm going to show some quick examples, and there's one I want to dwell on. This is one to the southwest of England. So this is, the green is the UCAR retrieval, the yellow is the retrieval I've been working on. One of the things I liked about this one is you can see that and the purple is the high resolution radiosonde. You can see that the RO is seeing this structure up here. The retrievals right now are not pulling it out, but the information is in there in the retrieval. Okay, next one. This is another one over Hilo. Again, things that are interesting to me. So the retrievals, the UCAR and the retrieval I've been working on are sort of in here, but there is information out there at larger bending angles that we've got to work on how to retrieve it. This is another example over New Zealand. Again, you can see this power out here, but the retrievals aren't grabbing it. This is an interesting one over Perth with some sharp structures, and they're tracking one another pretty well through here, not perfectly. But of course, the radiosonde is a point measurement. But I'm going to zoom in. The next one, I'm zooming in down in this area. So I've let the colors saturate because you can see some structure in here that's not getting caught in the retrieval, but the information's there. And one thing that caught my eye is you can't see it very well, but I've blown it up here. There is a strong peak right in here relative to the noise. So the noise is small here. There's a lot of noise in here because of the speckle. The signal's not so strong, so there's not so much noise. And it's actually, like 10 to 1 in terms of SNR in some sense. So I'm optimistic we can figure out how to retrieve that. Now, this is a really interesting case. I wanted to spend a few slides on this. This is Lahui, Hawaii. And so up here, everybody's sort of seeing the same thing, the sonde, the UCAR retrieval, our retrieval. And then the sonde is jumping over here to a large bending angles, fairly large bending angles. And our retrieval and the UCAR retrieval sort of stuck over here. It's not getting all the way over to here. But if you look at it, now I've zoomed in on this thing. I see this in a number of the profiles. You get these sort of vertical columns of noise. And this is the best one I've seen, where the rest of the profile is pretty clean. And there's one sort of noisy column right here. And if I eliminate that column, so I only use the measurements that are to the right of this column, I get this retrieval, which is much better matched to the purple that is the sonde. And so what I think is happening here is these low latitude occultations. We're in the north, our satellite's in the north-south plane. There's no sources over the poles. So our occultations tend to be off to the side at these low latitudes, which means they have a lot of horizontal motion. The tangent point is moving a lot. And so what I think is happening is I've drawn here the sequence of occultation planes. Well, it's a rising occultation, so it's going to the left. But what is happening, I think, is the occultation planes are sliding along, and we go over the Lahui, we go over Kauai, and suddenly we hit a column of convection. Oops. Go back. Suddenly we hit a column of convection, which is what this is. And so if I eliminate that, I get a much better retrieval. But it's also telling us why that's going forward. It's also telling us that the right way to think about this data is not a vertical plane. This is a sequence of planes that we're sliding through. And we should be thinking about this data more in a three-dimensional sense. A sequence of 2D planes, I think, is the right way to say it. And there's a lot more information in these occultations, I think, than we've been realizing when you think in those sense. And so I shouldn't be trying to do the weighting, the optimal weighting of at the different bending angles, because when you get to large bending angles, it's actually at different times. So these measurements over here were taken at a different time than these measurements were. So it's a completely different plane. One point I wanted to make here is just that in looking at these new retrievals we've been doing, we are getting a bit more of the high bending angles. The red line is our stuff, and the blue line is the UCAR retrieval. So hopefully we're moving in the right direction. So the preliminary conclusions, obviously this is a work in progress. There's a huge amount of variety of behavior. I think we're getting better than 100-meter vertical resolution. The high SNR is very important for the ducting detection, picking up the grazing reflections. What I've used it here for is capturing the large bending angles and reducing the negative bias at those bending angles. And to me, it's really important to have two wavelengths at high SNR, so you can see in all this diffraction noise, what stands out as being common at both of those. Yeah, we've worked on these retrievals, and we're making progress. We're actually profiling a bit deeper than UCAR. Noise, I think we're being dominated by speckle noise. This isn't thermal noise down there. We are seeing, and you can tell when you see these signatures of convection, you get these columns of noise. That example I showed was the one that stood out the best. I think we need to think in terms of sequences of horizontal planes when we do the retrievals. And one point I wanted to make, I know you guys are talking about buffer, but we need to allow, one of the reasons I'm saying this is as these planes shift, you can get a good bending angle at the same impact height that you got elsewhere in that profile because you're in a different horizontal location. That's a valid retrieval. And so I know you guys are in the middle of doing buffer, but I really think we need to think about generalizing this to get this information in. And next steps, it can do better in the weighting, but I think it's quite important to, like I said, move towards this three-dimensional, thinking more in 3 dimensions instead of 2 dimensions. And I think there's a lot of information about convection. Now that I've seen that Hawaii profile, there's a lot of information about convection and how well can we characterize it and how well can we remove it so that we can better isolate the bending angle profile and without that noise in it. Okay, that's it.
Thank you, Rob. This was a very good presentation. And I see Christian has a question.
Actually, one of your posters is, I've been thinking about this for years because of one of your posters. You were talking about all this noise.
I know, I've been thinking about that for years as well. And you could have drawn all these pictures 15 years ago if you would have taken the time to look into grass data.
Yeah, I have to say this is the first time I've really spent looking at the lower troposphere.
I know. If you go back to one of your pictures where you show your spectra, the interesting part in there is, so these are power spectra, a little bit one before where you have, one before. One more before, this one, perfect.
Okay.
So that is in the vertical, that is impact parameter. In the horizontal, that is the bending angle. What you see is that you have multiple power peaks at the same impact parameter.
Yes.
Many years ago, I called that impact multipath because you have multiple beams coming in. In our fundamental theory about wave optics retrievals, we assume that there are no horizontal gradients and there is always, ever, only one beam at any impact altitude.
Yep.
So this is where our normal retrieval breaks down. And what we do in practice is we try to pick one of these peaks and put a line through it and call that the retrieved bending angle.
Yeah.
And we probably, we do radio holographic filtering. That is with a smoothed version of the phase. And my guess is we are mostly sitting on the maximum of the power, and that's where we are drawing our lines through. So yeah, I agree. We somehow are going away from spherical symmetric situations, which our O can't handle, and we should have multiple bending angles. But then we also need to tell NWP people and others who are interpreting that how to interpret it, what it means that you have multiple bending angles from one measurement at the same point in time.
No, I disagree with that. What is it? Here's the point I want to make. Hang on a second. I'm going to switch to a different one because, okay, these lines right here are lines of constant time. Sorry, I didn't say this when I gave.
Oh yeah, sure.
So these measurements over here are taken at a different time and a different location. The beam has moved sideways. So what I'm saying is in each of these, we should do the bending angle versus impact height at each time and think of that as a plane. And in that plane, you only get one in that plane. But when you switch to the earlier time, you're now in a different plane. You're going to get a bending angle versus impact height, but it's assigned to a different lat long because the plane has shifted on it.
Still.
So that's the degree of freedom. The extra degree of freedom, I think it makes it work, is you get to move in lat long.
Yeah, you move it. But still, for every point in these lat long grid where you are calculating different impact parameters and bending angles, you assume that locally for that ray, you have spherical symmetry of the atmosphere, which you arguing you don't. So you're kind of contradicting yourself. I'm not saying, we had these spikes when you do that on all profiles, moving to the right in the spectrum, taking more data. In general, your statistics against NWP data gets very bad, very positively biased. And that's why we never did it, because our main customers are NWP people.
But you
have a contradiction there in your assumptions. That's all I'm saying. And
it's not a contradiction. It's not a contradiction to me. Each of those vertical slices, the white lines, each of those is a separate plane. So each of those has a lat long associated with it, and you can do a single profile in that plane. Over here is a different plane. I agree you have to invoke spherical symmetry to even interpret these results. You're stuck, you're absolutely stuck with that. But the degree of freedom I'm saying is you need to think about these as separate planes. So anyway, then when you get two strong things, solutions at the same impact height, that's actually okay, because this one occurred in this plane, this one occurred in this plane. They're physically separated, spatially separated. I knew I was going to trigger Sergey, so.
Yeah, sir, Sergey. Last question.
What was discussed previously, Rob, looks to me like underdetermined problem, 3D, because you have 1D observation. But that's okay. My question is very specific. When you're comparing actually wave optics retrieval to radiosonde, how you forward model radiosonde in the same, projecting it into the same space. If it's geometric optics, it's apples to oranges. I think wave optics modeling should be, forward modeling should be applied and speckle noise imposed. And then you will see maybe radiosonde will not look so nice.
Yeah, I completely agree. This is all geometric optics, just smoothed a bit.
Symmetric optics in spherical symmetric assumption, and you are trying to catch up with this with wave optics retrieval in non-spherically symmetric. It's kind of
yeah. Right. Well, and that's why I'm not worried about exactly matching the purple and the blue. I'm just sort of saying I can slide the blue over and sort of overall get it sort of to match the same bending angle, just in a rough sense. I completely agree with you. All right. All right.
I would like to thank all speakers of
Thank
this
you so much.
session. And we're going to go for lunch now, and we will be back at 12:35 for the next session.